In this video, we're talking about the photoelectric effect. So the classic experiment is that you're shooting light at a metal sample, and then you're looking for electrons that are popped off of that metal sample, and those actually end up creating a current that's detected in the experiment. In addition, you can figure out the kinetic energy of these electrons by turning up a potential difference across the gap between the metal sample and the plate that completes the experiment. And that potential difference is called the stopping potential. For example, if you slowly turned up the potential difference and all the current stopped when you got to 3 volts, that would mean the maximum kinetic energy of the electrons flying off the sample was 3 electron volts. In this particular question, we're told that no current flows unless the wavelength of the light is less than 550 nanometers. So this is without even including a stopping potential. What we've observed is that the minimum energy of a photon required to pop off electrons off of this sample corresponds to that wavelength of 550 nanometers. And that energy is called the binding energy for the metal target, or sometimes called the work function. That's the amount of energy spent just in removing the electron from the sample. So let's find the energy of these photons that are right at the threshold. That's HF, but we can use the speed, frequency, and wavelength relation for light, C equals F lambda, to replace F with C over lambda. And this is a fact that I derived in another video, and I'll post a link to it real quick. But as it turns out, in the right units, you can express HC as 1240 eV nanometers, approximately. And this is well suited to the way we get information when we talk about quantum mechanics and atomic physics. We're normally talking about wavelengths in nanometers and energy in electron volts. So I quickly get the energy of this photon, and that comes out to 2.25 electron volts. So that's the minimum energy it takes to remove electrons from this material at all. And that's called the binding energy, or the work function for the material. Next, I shift to a shorter wavelength of light. And this means I have enough energy to pop the electron off of the material, and I have some energy left over to give that electron kinetic energy. So to find that kinetic energy, I look at how much energy was in that photon. I'll write it this way: minus the energy spent on overcoming the binding energy to the material. So to start things out, I need the energy of this 400 nanometer photon, and using the same trick again, it's very quick. E is hc over lambda. Lambda is 400 nanometers. And I get 3.1 electron volts for this 400 nanometer violet photon. So this means the kinetic energy of my electron is the energy that was in that photon minus the amount that was spent on overcoming the binding energy. So I get 0.85 electron volts of kinetic energy. So what potential difference would stop this electron if it was headed straight for the opposite plate? All I have to do is create a potential difference of 0.85 volts. This means by the time the electron is approaching that plate, it's going to have an electric potential energy of 0.85 electron volts. In other words, all the kinetic energy has been converted to potential energy. The electron stops and turns around. So when you're doing this experiment, if you turn the voltage dial all the way up to 0.85 volts and suddenly the current stops, then you can conclude the kinetic energy of the electrons you're looking at is 0.85 eV. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.